We're going to look at a few real-life type problems that fit perfectly into what we're doing in differential equations, and one of those is half-life. So in case you don't know, let's just talk about what it is for a moment. The half-life of an object is the length of time it takes for 1/2 of the mass to disappear. Or that would be an object that is completely radioactive. Most things are not. That's why we still have things like bones and fossils and things of that nature. But what does decay in them is carbon-14, or that's the substance used for determining the age of something. So we call it just C-14. Has a half-life of, this is approximate, not exactly, 5,370 years. And we're going to use that as in carbon dating to see how old certain things are. So let's explain how this works. All right, so I have, I don't know, let's see, an object contains A grams of C14 initially. After 5,730 years, there is 1/2, or 50% of the C14 remaining. Now, this is not something I'm an expert on. The math is no problem, but how they determine the half-life is something I've seen it many years ago. It's something to do with how fast the decay rate is, or something like that. They're able to use a Geiger counter or something of that nature to determine that. Also, if you have, say, a fossil or a bone or something like that, and you find its volume, you can stick it in water, see how much the water rises, and that'll tell you the volume. I think based on that, they can tell how much C14 it originally had. And then from there, you can determine how old it was. Another thing that I know that is involved in these problems that we're not going to go into a complete detail of is the amount, or what happens to the C14. From what I understand is, in this 5,730 years, the C14 doesn't just disappear, it turns into an inert element, an isotope, if you will, that has no radioactivity, I guess, whatsoever. Like I said, those are not that's not important to me. Let's take a look at a problem and how this would work. Okay, so in year 0, say we have A of 0 grams of C-14. So in year 5,730, we have 1/2, or 50% of A of 0. In particular, I know that A of 5730 equals 1/2 A of 0. And a lot of times what we'll do is we'll call A of 0 will be used to represent A of 0. So an initial amount, if you will. Now let's see how much we have at any given time. I can turn this equation around and write this. I could say that A of t equals A sub 0 times 1/2 to the t over 5,730. That way you can see when t is 5,730, this will be A naught times 1/2. If t were 11,460, which is 2 of these, you would have 1/4 of that amount. And we're assuming this is all continuous. The following equation says dA over dt equals k times A. That is, the change in the amount is proportional to the amount. So we'll make use of this stuff in a minute. What this means, if I go to solve this equation here, then I have dA over A equals k dt. And then what I'm going to do is integrate both sides. And I'm going to go from 0 until now, which is t. dA over A equals k integral 0 to t, as long as I do the same thing to both sides. Now, it's not a good practice to put d of t because the limits of integration are in t, so I'll use tau just as a placeholder. Those things don't matter. It's what they call a dummy variable anyways. But let me go ahead and integrate both sides. I have the natural logarithm of A. Now, the amount is never going to be 0 or negative, so I'm not going to worry about the absolute value of this. And that's going to be from 0 to t will equal k tau from 0 to t. And that gives me the natural log of A of t minus the natural log of A of 0 equals kt. Let me use property of logarithms to rewrite the left side as the natural log of A of t all over A of 0 equals kt. I'll take e to both sides, and so I'll get A of t all over A of 0 equals e to the kt, and I'll multiply through by A of 0. Remember, A of 0 is the same as A sub 0. So this is the formula we're going to use for, well, actually, to be honest, this formula works for exponential growth and decay. So this is kind of a lot more than we need to do our problem. In fact, you could, without appealing to differential equations, you could work this equation and get the job done. And after deriving this equation, I am not going to use any differential equations anymore in solving these problems. So the real part that involved the differential equation was right here. These type of problems of this nature are the ones that we're going to look at in this particular section. Those that are proportional to how much is left over. So let's do an example. Let's say a bone is dug up and it is determined to have 1% of its original C14. How old is the bone? And so we're going to appeal directly to this equation here. And first we have A of t equals A naught e to the kt. We know this information. Since we're using C14, C14's half-life is 5,730 years. So we know that A of 5,730 equals 1/2 of the initial amount. So let me plug that in. A of 5,730 equals A naught e to the k times 5,730. And like I said, I know this side to be equal to 1/2 A sub 0. And at this stage, I'll divide through by the A naught. And then what I'll do is I'll take the natural logarithm of each side. Since this is all going to be done on a calculator, I'm just going to go right to decimals and not bother with fractions anymore. And now I'll divide by 5,730. K, you should know, is referred to as the constant of proportionality. It stays the same throughout the entire problem. So now if we want to know how old this thing is, we would like to know when it was whole, or how many years have passed until we got to this 1% mark. So really, we want to determine t so that A of t equals 1% of A sub 0, or that is 0.01 of A sub 0. Okay, now this, I'm going to use that in the problem, but I'm going to refer to it as K because it'll get too cumbersome to do anything else while you're working the problem. So anyways, let's go ahead and throw these into the equation. I have 0.01 A sub 0 equals A sub 0 e to the k t. As before, we'll divide through by A sub 0. I get 0.01 equals e to the kt. As you can imagine, take the natural logarithm of each side. And then I'll divide by k. And k, let me go ahead and plug it in now. K was ln 0.5 divided by 5,730. So this will turn out to be 5,730 ln 0.01 divided by ln 0.5. And from here it's a calculator exercise. And we find t is approximately 38,069 years. I wouldn't bother with decimals or anything like that. I mean, the 5730 is not absolutely positively exact anyways. And when you're dating such old things, I don't think it matters if you get these down to the day, minutes, and second. So there you go. And there is how the process works. So what is the main thing you want to take away? You can do one of two things. This is an easy formula to memorize. I have never had a problem with it. But whenever you're talking about exponential growth or decay, This formula will work for all of that. And it just so happens that half-life problems are problems involving exponential decay. Exponential growth might be something like bacterial populations or animal populations or something like that.